We're just waiting a couple of minutes to give other people a chance to come and join our session. I just wanted to thank you all in advance for joining in. I know that times are a bit crap for everyone worldwide right now, so it makes me feel really grateful that you took time out of your day to come and hang out at SourceCon, come and see this talk. I hope it's useful to a lot of you. If you have any problems hearing me or what have you, just make sure to drop it in the chat. I just wanted to let you know that I won't be taking any questions during this talk, but you can go and drop them in the Internet Wizard channel on Slack, and I'll get to them after the talk. Alrighty, let's get started. I would like to acknowledge the Jagera people, traditional custodians of the land I inhabit. The Australian slang yaka meaning work, comes from a Jagera word, yaga, which means the same thing. I'd like to acknowledge all of the work that the Jagera people have had to put in to be recognized as the traditional custodians of the land and recognize their continuing connection to the land, waters, and culture. And I'd like to pay my respects to elders past, present, and emerging. Now, I would like to welcome you all to your first day at Unsourced University, the premier magical institute in the city of Test Morpork. I am the Wizard of Oz, Australia. You can call me Professor Lacey. That's L-A-E-C, silent lightning bolt, E-Y. And I'll be teaching you construction and application of hypertextual information systems, which beings on the lesser spheres call the internet. As the internet is now available on computers, it is a form of the mathematics known as algebra, or mathematics. It's a form of magic. Words. Everything that happens when using the internet is predictable and logical, even when it doesn't feel that way. Once you grasp the arcane knowledge I will impart upon you, you will have a greater understanding of how the internet is put together, giving you debugging skills far greater than lesser mortals. Also, this course counts for 40% of your overall yearly grade, and those who fail will have to clean out the unicorn stalls all of next semester. Moving on. The online Visibo portal contains a copy of the slides and a couple of cheat sheets. And we shall start at the very beginning, a very good place to start, with the request that kicks the entire thing off when you enter a website address. The magical term for a website address is a URL, short for Uniform Resource Locator. By the way, I'm afraid I won't be going too deep into what these acronyms mean. Mostly it doesn't matter. If it does matter, I'll try to give a quick overview. Somehow, when you enter URL, it makes your browser load an entire web page. How does this happen? Through magic! And also science. Mainly it's science. A URL contains all the information a browser needs in order to contact, find, and make a request to the server that has the resource that we want. We'll talk about the other parts of a URL later, but to find the server, all we need is the domain name. That's this bit here. It's composed of chunks called hosts, and the hosts are separated by dots. The very first host is often called the subdomain, and the last is called the top-level domain, or TLD. Domain names are like other addresses. You have to follow them from least to most specific to get directions to a place. For instance, if I send you to the library, you can use a series of campus maps to go from the largest area, the university itself, to the smaller area, the specific part of the library I want you to go to. A signpost at the campus entrance directs you to the Minotaur Quadrant map. A map in the Minotaur Quadrant directs you to the library building's information desk. And finally, once you get there, you can ask for the annex you want. This is called a recursive process. We perform the same steps over and over again until we get our result. Directions for a domain name are also developed through a recursive process, but what we're looking for is a thing called an IP address. It's a series of 4 numbers, all under 256 value of 256 for arcane reasons, separated by dots. You can see some examples on the slide. The reasons why it's under 256, not really that important. The process of finding an IP address is called resolving, and it works through a technology called the Domain Name System, or DNS. When your operating system needs to find an address, it reaches out to a server called the DNS server. This is usually in your organizational network, but may also be in your ISP or on your router. That server knows how to find the server that can find, so knows how to find the maps for all the top-level domains. Those maps are called name servers, and each top-level domain has one dedicated to it. Just like with a physical direction, we go through the servers recursively, checking the maps until we have directions. So to start with, we know where the MPRK name server is. So we go to its name server and go if it knows where the whole domain name is. It goes, no, it doesn't, but I do know where the EDU server is. Go and ask it. Next, the DNS server will ask the EDU name server if it knows the location of the IP address. Again, if it doesn't, it tells the DNS server to ask the next server, providing the address of the USU server. Finally, the USU server is the authoritative server. It's the server that's been configured directly by unseen university staff with the right IP address for the domain we're going to. The USU server can return the address directly to the DNS server, which then returns it to our operating system, and then to the browser. So now we've converted the domain name into an IP address, we know where we're going, we can make our request. Digital systems communicate requests through a series of predefined rules called schemes or protocols. A URL starts by identifying what scheme it'll be using. The URL we looked at earlier shows that we're using the HTTP protocol, and this is the main protocol that browsers use. HTTP is a unidirectional request-response protocol. Now, that's just a complicated way of saying that the browser must send a correctly formatted request to the server before each response. The server cannot contact the browser, it must wait for a request, and the server must send a correct response to the server to the requester in a timely manner. I apologize if I stumble over my words a little bit. It's 10:30 at night here. An analogy is in order here. The Unseen University Library is staffed by clockwork golems with no personality or memory. They also use a unidirectional request-response protocol. They only come to life once you ask them for a book. The way you request a book is you politely ask for it by name and author. It will then check if you have the right to borrow it, fetch it for you, and give it back to you. You can't fetch multiple books at once. The golem will fetch the first book, assume you no longer want to receive that book, and then fetch the second book instead. It will also never respond without a request. It's literally impossible for it to do so without violating the laws of causality. A reminder that violating causal law on campus can be met with severe fines, expulsion, and the risk of becoming your own grandparents. HTTP and the golems are also stateless. A stateless connection is independent. Past or future connections effectively don't exist to the current connection, and no reference to the current connection will be kept after it's finished. Please excuse Professor Galena here. She's not transformed into cat form, she is just a cat, and she does what cats do, which is whatever they want. We can best understand how stateless servers work again with an example. The library golems don't maintain state between requests. You have to include all the information you need to find a book at once. You can't refer to the same author as a previous request because the golem doesn't remember what the previous request was. Now, this seems like a contradiction because a web page knows when you've logged in, and when you add things to a shopping cart, they stay in your shopping cart. If previous requests don't exist, then how does this happen? Through wizardry! But we'll get to that later. First, we're going to dissect a HTTP request. Dissecting the library golems, not recommended. This here is a HTTP request. The first line is called the start line, and it tells the server what we want it to do. The bit in the middle is the path and query string from our request, and it tells the server which resource we want it to operate on. If we're just going to a standard page, like a home page, there's no path or query string. And so we request the default resource, which is represented by a backslash. At the end, we've got a HTTP version, which is basically irrelevant for our purposes. And at the start, we have a HTTP verb, which tells the server how we want it to operate on the resource. Here are the common HTTP verbs. A GET request is what your browser does when you first open a URL. It tells the server, please give me this resource. A post request lets you add information. It's what you use when you submit a form or save a document. A pull request is similar to post, except it's idempotent, which means that no matter how many times you do the same request, the results will be the same. This might be if you save somebody's phone number. If you save the same phone number over and over again, the phone number won't change. And delete requests are pretty obvious. Developers get to choose how their servers respond to different verbs, which does mean that sometimes they configure them wrong. The next part of a HTTP request are the headers. The start line tells the server what we want it to do. The headers tell the server how we want it to do it. They're optional, but these three are almost always included. The host header tells the server what domain name we're requesting content for. We need this because one machine with one IP address can host multiple servers. So if this was missing or absent, you might get content from a page you weren't expecting. The user agent header tells the server what kind of browser we're using. This is how a server knows to, say, return the mobile version of a site, or what features the browser supports. If you get this wrong, that's how you get a mobile site on your desktop, or a desktop site on your phone, for instance. And the accept header is a little bit more complicated. It tells the server what format to respond in. For a web page, this will be HTML, but sometimes you might want XML, or an image, or music. If you get this wrong, you might get a server error, or you might just get a page of garbage instead of a web page. Finally, the request has a body. It contains any informational, that's a combination of additional and information, which is what I meant to say. It contains any additional information the server might need to process a request. There's no set format. It can be structured however we want. So, we've built a request, we know where it's going, and we're ready to send it. How does that happen? Network connections are a nested series of, it's your problem now. If your computer is located on if your computer is the same machine that the server is on, you won't go across the network. That's called being on localhost, and it's the fastest kind of connection. Mostly though, your server will be on another computer. That computer might be on the same network, say in a corporate data center, and then the connection will have to go through the switch. If it's on another network entirely, say over the internet or across a VPN, your computer will contact a server called a gateway, which will contact its own gateway, and so on and so forth until it finds a path across the networks to the server. But wait, there's more. Remember that I said HTTP is the protocol that we're using here? Well, HTTP doesn't belong on its own. It's called an application layer protocol, and it doesn't care how it's actually transmitted. That belongs to the transport layer. Generally, HTTP goes across the TCP transport layer protocol. And that one doesn't care how its requests are transported. They get sit on top of the internet layer. The internet layer is generally implemented with the IP protocol, and that's where those IP addresses come from. But do you see the arrow? Do you see the arrow there, roughly? There are more layers under this. Several. Do they matter? No. For most QE purposes, knowing that both HTTP and TCP exist, because they're the only errors you might accidentally see bubbled up in your browser. In a really well-coded app, you probably won't see these at all. You'll just get a nice error page saying, we're sorry. There is, however, an alternative for all of these protocols, and I'm going to take a little diversion to tell you about it. It's called IPOAC, IP over Avian Carrier, that is, Pigeon. It's a proposed standard with a standard number, RFC 1149, and it has two proposed extensions. It works by attaching data in the form of flash drives or a piece of paper to a pigeon leg, a homing pigeon, and then releasing it. Despite the fact that it has high latency, when using flash drives as the underlying mechanism, IPOAC can reach higher speeds than broadband. An Australian experiment with a car, a pigeon, and an ADSL connection over 132 kilometres by road. For those of you who use Imperial, 132 kilometres is, I think, 8 gallons. Anyway, the pigeon finished in 1 hour and 5 minutes, the car finished in 2 hours and 10 minutes, and the ADSL connection did not finish. It disconnected twice and then didn't come back online. The good thing about IP over AV and carrier is that collisions are unlikely between packets, but there is a risk of loss, particularly to raptors. There's one more thing that controls how requests travel from the browser, and that's proxies. By the way, if you're sitting here thinking that I made all of that up, I didn't. 100% real. Back to proxies. Proxies are a machine that sit in front of a network and control what traffic can come in and out of that network. They're commonly used to provide internet access in a corporate network or to restrict access to an internal server by a specific route. Requests through a proxy work a little bit differently. Instead of connecting directly to the server, the browser will ask the proxy to do it on its behalf. This is where the name comes from. That includes resolving the DNS address, which can provide inconsistent results. If the proxy uses a different DNS server to the computer, it might resolve the address entirely differently, or it may not be able to resolve it at all. Applications can also be configured with individual proxies. It's possible to configure an entire system with a proxy at once, but it's also not uncommon for some applications to completely ignore it. Java in particular loves to just give your proxy the finger. It's also possible to configure applications to only use proxies for some servers and not others. This is something to keep in mind if you see odd connection behavior from apps on the same device. So now that we've left our network and come towards the receiving network, we run into some unfortunate realities. Servers have processing limits. They have network limits. They have minimum transport distances. They break and they require upgrades and they get overwhelmed. There's 3 general technologies that we use to compensate for all of these. The first one is an Anycast IP address. It acts like a magic mirror that always lets you see where the nearest princess is. And now that I've said that out loud, that sounds really creepy. I rescind that analogy. Multiple servers can have the same Anycast IP address, and when you request that address, the underlying network hardware of the internet will check to see which server is closest in terms of network distance and return a connection there. For instance, I'm in Australia, and if I request gmail.com, I don't want to get the Gmail server over in West Germany or Eastern USA. I want the one in Sydney. The Anycast address will make sure that I get there. The next technology is called a load balancer. It's a technique for sharing load, which is the work that a server does, across multiple identical versions of that server, each running a copy of the application. Work is assigned to them roughly equally. There's a few different ways it can happen. It's kind of like having a pool of apprentices making potions for you, but selling them as though you made them yourself. Which I would never do and which you definitely can't prove. This can also help if one server becomes overloaded with a long task or suffers from an operational error. Tasks can just be assigned to the well-behaved servers. Load balancers can cause problems if one of the servers isn't running properly. Perhaps it's hungover, or it's reading from an older version of the textbook, or it's distracted by flirting with the attractive werewolf exchange student, Darren. I mean, maybe it has a bug, or is using an older version of the code, or doesn't have the same processing capacity as the other servers. Finally, we use CDNs. A CDN is used to place a copy of content closer to the end user. A good example is Netflix. They store copies of all of the movies and shows all over the world, so they can directly use a load from the closest one, making it load as fast and as high quality as possible. A lot of sites use this to serve fonts, libraries, and images. So, we've made it all the way across the network, through the Anycast forest, down into the dungeons of the CDN, and now the server in question is about to be contacted. But what exactly are we contacting? Well, demons. No, really. Every web server is possessed by demons. Because demons are the name for a program that runs continuously, waiting for requests they can fulfill at a cost. Thankfully, these days, demons tend to feast on ad revenue instead of mortal souls. However, they're still capable of making a developer's life hell. If a demon is banished, not summoned correctly, or tries to possess the same part of a server as another demon, it might not serve pages correctly. We're not going to go any further into servers because they're infernally complicated. But just remember, whenever you're online, whether you're reading a funny website, doing your accounting, looking for love, or looking for love substitutes, everything you do is being watched by the demons. Moving on. Once the demons have rent the flesh of our request and completed their eldritch processing, they'll send a response. This is one of the more troublesome parts of the process, because every system involved in sending the request created a connection and kept it open, waiting for the response. So the browser and the server and the proxy and the internet router and the ISP and the underwater cable and the transcontinental backbone and the edge router and the load balancer and finally the server are all waiting for a response. These connections won't last forever. Each has a maximum duration. You can see this request has taken 25 seconds by the time it was opened. It'll take roughly 25 seconds for the response to go back. That means that the server only has 10 seconds to actually finish its processing. Otherwise, the browser will close the connection, assuming it broke. Sometimes networking equipment can have its own timeouts. It's not uncommon for a proxy to feature, say, a 30-second timeout. So even though the browser might still be happy to wait, the proxy isn't. The server can't respond because it can't create connections, and the proxy is just going to return errors all the way up to the computer in question. Bummer. Let's assume, though, that we actually got a response. HTTP responses are formulated like this, and this looks an awful lot like a HTTP request because they're pretty much the same. We have a status line, which tells us whether and in what way the response was successful. We still don't care about the HTTP version. Instead, we want to know about these two things, the status code and the status text. Status codes and status texts are a set of predefined responses, and they let the browser know whether a response was successful and in what way it was successful. You probably know the most famous one, 404, file not found. What you usually want is 200 OK. That means that the request worked perfectly. And here's an incredibly dorky way to remember that, about which I am not at all sorry. You can make 2 OKs at once with both hands. There's 2 thumbs, making 2 zeros, 200. OK! All right, I'm a little ashamed of that. Moving on. I included this cheat sheet in the resources because roughly knowing what category everything is in is usually sufficient for QA purposes. I like to remember them like this. The 100 series is informational. Please hold. The 200 series is successful. Here you go. The 300 series is redirects. You go here. The 400 series is a client error. You screwed up. And the 500 series is a server error. I screwed up. Developers get to choose which code they can return from their server. And this can introduce bugs because that changes how the browser interprets what it should do next. For instance, 4118 I'm a teapot is an actual HTTP status code. It should be returned by an internet-enabled teapot when asked to provide coffee. However, the standard specifies that if the device is a combined tea and coffee pot and it's temporarily out of coffee, it should instead return a 503 service unavailable. These meanings are very specific, and you need to be careful not to use the wrong one. Back to our HTTP request. The response also contains headers, and much like the request headers, these say how the response was fulfilled. These are the most common ones. The server header tells the browser what kind of daemon processed this request. Unicorns are a real type of daemon used by Ruby. See, the description promised you they'd be in here. The content link tells the browser how long the response is, which lets us check for bugs. And the content type tells the browser what format the response is. If your page is rendered as a bunch of XML instead of text, or if your browser attempts to download it instead of opening it, the content type is probably wrong. The final component is the body. It's the meat of the response. It's the actual content requested from the server. For a web page, this will be HTTP. But if it was a file, for other HTTP responses, it may be a file or XML or anything else that we wanted. So now we've got it, we can render it. We've got HTML back. HTML is a language that contains the text of the website along with information about how to display it. It's like an all-in-one potion kit. It gives you the Eye of Newt and extract of Chameleon Karma and tells you to stir them widdershins under the light of a gibbous moon. Everything you need, already included. The brewing of a visible web page from HTML is called rendering. HTML is composed of blocks called elements. If you've ever hexed a browser with Selenium so you can automate it, these are the same elements that you were referring to when interacting with. Elements can be nested inside each other, and they're delineated with tags. Most of them have a start and end tag, like the P tag here, but a couple, like the BR tag, stand alone. Tags can also contain attributes, like the element's true name, also known as its ID. This HTML here describes a heading, followed by a paragraph. There's a line break and a single piece of text that's strong, which is the modern way of saying bold. Once it's rendered, all the tags are missing, because their only purpose was to provide structure. The BR tag was replaced with a single line break, and Binky was made bold. But all the other spacing has been stripped out. It needs to be explicitly included in the HTML, otherwise it basically doesn't matter. This is where we've got another bug. There's no space between apples and blimey at the base, because although blimey was on a new line, it didn't have a line break before it. It only had an actual line break. It needs the tag. Now, rag and bone blocks of text are all good if you're making a website for an accountant in 1996, but it's the 21st century and websites have images now. And this is where HTML's next trick comes into play. It can pull in other documents. When the browser encounters a request to those documents, it'll make another HTTP reference to fetch them, process their content, and apply them to the page. Let's include other technologies like CSS and JavaScript, and that's where the magic happens. Well, okay, that's where further magic happens. Once the browser has used HTML to decide how the page is structured, CSS controls how it's styled. It uses things called CSS selectors, which you've, again, probably heard of if you've used Selenium, to decide which elements to impact. Selectors can describe an element by tag, ID, attributes, or position. Since only 12% of our students this year are immortal, I'm not going to go any further into the cryptic morass that is CSS because it's very complicated. But here's a very short example. We're making the header surrounded by a yellow box. We're making anything strong, light blue, and we're making the text itself, Comic Sans. I guess some sort of demon wrote this. The third part of the weird sisters of websites is JavaScript. It is the programming language of the web for two main reasons. It is a fully featured programming language that runs inside the browser by default, and has full access to the entire content of the website programmatically. It knows what the user's doing, it knows what data is entered, and it knows how the page is structured, even as changes occur. This is how JavaScript can interact with the entire page and create a dynamic, fancy, modern experience from a normal, simplistic website. What does this let developers do? Well, have you ever used a website that lets you save a form without reloading the page? That was JavaScript. Has your internet banking ever told you to take some action or it would log you out? That was JavaScript. Has a page ever auto-completed your search terms or hit you up with a paywall or disabled a button until you entered a field? JavaScript, JavaScript, JavaScript. This power comes with great responsibility because JavaScript might be the one thing that spins your site together. A problem with one part of a site's JavaScript might spread out in a web, stopping all the scripts on a page from working. This could break forms, cause text-to-speech services to malfunction, prevent logins, lose data. Because it could have been used to implement literally anything, problems with JavaScript can cause literally anything on your page to malfunction. Just enjoy this slide for a minute. This wine is very good. The marketing team didn't make me put this in, I'm just sucking up. Give myself good feedback, like and subscribe. Moving on. Remember earlier when I fobbed you off about how cookies work? Well, now it's time to reveal that it is all a trick. Sorry, an illusion. Browsers and HTTP work together to make states exist by building them on top of HTML. HTML is totally left out of the process. When a browser visits a website, the server processes the request and creates a record in its memory, which it calls a session, and it attaches a value to that session called a cookie. It returns that in a header called the set cookie header, and the browser stores that in memory. Every time the browser sends a request to that server, it will include the cookie in the cookie request header, and the server will remember and recognize the browser. If the browser doesn't send the cookie because it was cleared or it expired or was removed by a proxy, which is a thing they can do, and another reason I don't like proxies, the site will treat the browser as though it doesn't know who it is. If another device gets a copy of your cookies, they could impersonate the first browser with potentially disastrous results. I want to go through a couple of optional technologies that make websites a little bit better, but I am running out of room, so I'm going to have to speed up a little. Background requests are a great technology because in the olden days, when somebody interacted with the form, they'd click a button and the entire page would vanish as it went off to the server, chugged away, and came back. Everything was janky and it sucked. Now we have XHR. XHR is a technology that lets the browser make a request in the background controlled by JavaScript. JavaScript can watch what the user is doing on a page, send a request to the server without doing a page load, get the results back, and use the DOM to update the page while the user is using it. And this kind of background processing is now at the heart of almost every modern website. There's one example that uses entirely background processing called single-page applications, which I'm skipping through because I'm all done, or because I'm almost out of time. But I want to reveal one more thing, the deepest secret of all. Everything I said was a lie. For a good reason. The internet is really complicated. Every technology comes in multiple versions. There are multiple implementations of technologies, and even the weirdest tiny thing can have an impact on your app. There are more updated standards that people don't use. There are replacements that are rolled out invisibly, and there are network technologies that will ruin your day. Edge cases and tricksy hobbitses and cursors and magic mirrors and caches and CDNs. And you might be tempted to give up and cast ignorance and throw everything in the bin, but please don't. You can rely on others. None of us know everything, and you can learn some of it, I promise you. You can brew your own web servers, and you can read your status codes in the tea leaves, and study the grimoires, and become an apprentice. The internet is the most fundamentally disruptive, enriching, transformative thing since fire. It makes things more convenient. It makes us feel less alone. It helps us find our people. It changes everything. It really is magic. It's magic, and you can be a wizard. Thank you very much. If you'd like to find a copy of these slides, you can do so in the Bizzabo platform or go to bit.ly/BANetWiz, where you can download them from a Google Drive. If you have any questions on this talk, go to Internet Wizard on the SourceCon Slack. There's a great introduction to how cookies work in that first link, and there are some delicious cookies you can bake in that second link. If you want to follow me, I'm on Twitter and GitHub, and if the baking caught your eye, I have an internet cooking show over on Twitch at Dylan Tonic. Thank you so much, and I hope you enjoy the rest of SourceCon. And as is custom now, stay safe and be well. Bye.